Quantum entanglement is perhaps the key to understand quantum physics. It is a phenomenon that sets quantum physics apart from classical physics. Many people would argue that quantum entanglement is the most important phenomenon in nature. Yet there is this outstanding mystery that no one has explained what it really is. Today we are going to solve this mystery that has been around for about a century. We are going to describe exactly what quantum entanglement is, where it's located, and why it's here. If you found this video, you probably know the history, but I go through a super short historic background. Entanglement has been discussed since the beginning of quantum physics in the 1920s. People like Einstein and Bohr have had different views on what it really is or implicate, and scientists still do. In around the middle of the 60s, Bell came up with a famous experiment, where after ingenious thinking a bunch of math, the result basically was that entanglement is non-local information. Scientists talk about local information of an object, meaning information that can be measured directly from the object. Some scientists, for example Einstein, have historically argued that all information affecting the behavior of an object must be local, and that an interaction can only involve local information. But Bell showed that this is not the case for entanglement. If you Google quantum entanglement and look for the images, you get an idea how entanglement is thought of today. Generally, it looks like something like these two examples. It is pictured as something mysterious, a lighting energy between particles or some field that connects entangled particles. But entanglement is not mysterious. It's not some kind of energy. It is not a field. It's not faster than light communication. The connection between entangled particles are much simpler and not hard to understand. It all comes down to information. Now, information in science may sound abstract to you, so how should you think about information? How should you approach this concept? I think it's a good idea to see upon information as a detective look upon a crime scene. As a detective, you have to get information from wherever you can and in many forms. It's not always the butler. You may notice a footprint, some textiles under the nails of a victim, even a fingerprint, or the sense of a strange perfume. All those observations give you information of what has happened. Imagine you are a detective entering a crime scene, and at once you see a bullet hole in the wall. When you examine the bullet, you notice its caliber and some scratches from the gun's pipe. The caliber and the scratches are examples of local information. It's local information in respect to the bullet. It can be read or measured directly from the bullet. But then you examine the hole in the wall. From that you can determine from where the bullet came. That information was caused by the bullet, but you can't read it on the bullet. It is non-local information in respect to the bullet. It is path information. So now you figure it out. Properties like spin and electric charge are local information of a particle, and the non-local information is the path. Now, we only talk about entanglement if the path is divided. So if you have a quantum system with divided path, entanglement is that divided path. Entanglement consists of a number of subpaths that all originate from a common interaction event. More precise, entanglement occurs between properties, not particles. It is properties that are created at the same event that becomes entangled. That properties are created at the same event is the only physical connection between entangled particles. This is how you can illustrate entanglement. The divided path is non-local information, and the property information is local but spread out between two or many locations. In this case, just two locations. The information in these locations are exactly the same. Each of these locations have information of all the possible outcomes of an interaction or measurement of the system. The fact that all paths originate from a common interaction is important, because we then only need the principle of conservation of information to explain the outcome when the entangled state collapses at a measurement. The correlation entanglement that has been so mysterious for many scientists emerged between properties because they have been created together and are restricted by conservation of information. Any combination of properties within a particle or between particles that have a common origin are entangled, and it is extremely common in nature and happens a zillion times at the blink of an eye. Whatever are created together will become entangled. Another question that scientists have been trying to get an answer to is if entanglement is real. So what do you think? Is the divided path of a quantum system real? The divided path is spread out over both space and time. It represents all of the past location and gives all of the future paths when the system is measured. Entanglement or all path cannot be directly measured in any experiment. If we try, the system will collapse. The path is also an abstract concept that has no physical form at any time. So we can say that entanglement is not real in those senses. However, at collapse, all paths are effectuated and becomes real in the sense that all paths influence the future. So we can say that entanglement becomes real at collapse. All behavior of entanglement can be understood from two principles: conservation of information and information efficiency. The first principle, conservation of information, reflects a symmetry that underlines all symmetries in nature. Whatever transformation or interaction you do, information will remain constant. You can simply say that you cannot create something from nothing, and something is information. So everything can ultimately be regarded as information. Everything is just different forms of information. The second principle says that nature always chooses the most information-effective way in any situation. In what we can describe as a decision, nature always chooses the way that uses as little information as possible, both in making a decision and executing a decision. For a decision to be maximum information efficient, it must be made randomly. Any information in a decision rule would not be information efficient. It would use information, and it would also take time to effectuate or execute that information. Information can be seen as nature's resource. Random decision of the maximum efficient way to make a decision, and it will be effectuated instantaneous. At, for example, a beam splitter, environment conditions allow two possible paths. Both these paths are executed, because it's more information or energy efficient to send all possible outcomes in both paths than send specific outcomes in each path. You are probably more familiar with spin entanglement, where both paths carries the information spin up and spin down. It takes less information to store spin up and spin down than, for example, just spin up. This may sound strange to you, but it is so because nature stores information as a superposition of waves. And the more spread out the system is, the less waves are needed to describe the system. A peak in space or time requires infinite numbers of waves in all frequencies to describe. So any spread out, even if it is two values, represents savings in information. This is the reason why waves spread out whenever they can. Within the restrictions that the environment imposes, waves will always spread out due to information efficiency. At collapse, all future outcomes are locally available, and one randomly appear. Just exactly one due to conservation of information, and random because it's the most information efficient way. And if the decision was not made random and instantaneous, the outcome would violate conservation of information. So information efficiency is imposed by conservation of information. To sum up collapse, through a random decision made locally at the interaction under restriction or conservation of information, nature knows instantaneous where and at what value or location of an entangled property will appear. You can pay special attention to the fact that only local information is active in the interaction. The only thing missing is the future path, and that is achieved by all the paths of the entanglement. So the decision is actually made locally, but to effectuate it, nature uses all the paths that are non-local in respect to the interaction or measurement. You could say that Einstein was almost right, as the decision is made locally in an interaction involving only local variables, but the outcome is also dependent on the paths. Notice that there are no action or information involved to effectuate all the paths. They just go on independently of the interaction. Entanglement is the result of an interaction, where entangled properties arise because they are created together. Collapse or measurement means that another interaction rearranged the origin. Some entanglement are broken and other appears, and overall entanglement is increasing in the universe. Information conservation in collapse means that total information in the collapse property must be the same from before entanglement as after collapse. At collapse, a property locally gains information, for example, gets defined location or defined spin. This gain in information is accomplished by increase of entanglement somewhere else. So the collapsed particle's wave function carries more information than the entangled particle had. And you need all the paths to describe its past. Because the collapsed wave function carries more information, it will be less spread out. Especially in location entanglement in some split experiment, this can look dramatic as a wide particle wave function, instantaneous, is transformed into a narrow top when it collapses. This image can illustrate location entanglement, where a particle appears at a position away from the interaction. When properties are entangled, they are useless energy. That energy cannot do any work. The system have to collapse so the properties become untangled. Then they can do some work. So entanglement is entropy, but it takes useful energy to untangle the system, and that useful energy ultimately comes from other properties being entangled. So entanglement and therefore entropy is always increasing in the universe. You can also analyze entanglement as a communication problem. In this case, the creation is the source. The measurement is the receiver, and all the paths is a communication channel. Entropy has been introduced in different contexts, even if they have some differences, and for Neumann entropy might be the most fundamental. They all come together in entanglement. Many synonyms have been given to entropy, from amount of disorder, uncertainty, or not useful energy in classical physics, surprise information in communication, hidden information, and many more, but they all fundamentally describe entanglement. Just different vocabularies from different fields in science in different contexts. The reason why there are so many definitions and names for entropy is probably because it's a concept that's rather hard to understand. And as it is so fundamental, it appears in many circumstances. And yet we have so far not included gravity in our description. That is for a coming video. We shall go through a quantum experiment step by step in the following episode to illustrate all stages of entanglement. After that you will have a more concrete notion of entanglement. In explaining quantum entanglement, we have also solved the measurement problem. You can notice the several existing candidates to explain the measurement problem violates the fundamental principles of entanglement that we have just described. In popular science, it's often mentioned that a particle can be at two places at the same time, often illustrated with something like a person sitting in a bar and dancing on the floor at the same time. But this is a false and misleading image. To observe a particle at two places at the same time would violate conservation of information. When all possible future states are stored in multiple locations in entanglement, they cannot be measured or observed, because if we try, the wave function would collapse. So you cannot observe a particle in many positions at the same time. In the historic background, I could have mentioned the thought experiment EPR after the three authors, Einstein, Podolsky, and Rosen. In their paper, they argued that entanglement can be explained by hidden variables. Bell's experiment is a way to prove that there can't be any hidden variables. But this follows already from the principles of conservation of information or information efficiency. Obviously, it's not information efficient to include hidden variables. If you think through the hidden variables proposal with conservation of information, you realize that it is impossible to, by experiment, separate hidden variables from the obvious alternative for nature to randomly choose fixed values for the properties at creation. So if hidden variables existed, entanglement would not exist. And entropy, well, you get the picture. Since this is the first video for this channel, I thought I should show you what you can expect in the coming videos. There will be a second episode on entanglement, where we will analyze a classical experiment called the bomb experiment. Apart from illustrating entanglement step by step, it will show how important it is to include entanglement and all the historic paths in your analysis of an experiment. If you don't, you end up thinking that you have information of something that has not happened, and that would violate the principle of conservation of information. Also coming is a video on how gravity is related to the standard model, and the basics on how to unify this in the common theory. Or, in other words, how to unify quantum physics with gravity. This seems to be a major question in fundamental physics today, but to my knowledge not so much concrete results have been published, like a fundamental equation, so I think we can do better. Maybe the format can improve, or hopefully it can improve in coming videos. But focus will be on depth in the subject. Yet it should be relatively easy to follow and understand. No complex math, for example. The thought is that there be a series on the fundamentals in nature, but it's also up to how the response is, how this forum works. So if you are curious on how the universe operates at the most fundamental level, make sure to follow this channel. If you like this video, tell a friend. Maybe you know someone who's longing to know what entanglement really is. I have also set up a page on Patreon. If you like what I'm doing, consider to support me by becoming a patron. That was all I had for you today. Now remember, it's not the goal that counts, it's the path. So thanks for your time and interest, and I hope to see you back on the next episode. Bye.